I don't know if you can see my screen.
Yes, Doc.
Okay,
Oh,
so
we can see.
if you recall, so if you recall from the first law, we just wanted to see how we can measure heat, because we've seen the differences between heat and then temperature. So we try to see how we can measure this, or well, the calculations which involve heat, which we says that is just equal to the internal energy plus pressure times the change of the change in volume. So I remember we did one or two exercises before leaving, and so that's where we tried to end. Well, today we want to continue and try to see how we can really actually measure this heat. Well, I think the last week we also saw the difference between heat and then temperature. So that's just what you are trying to do. So we again establish the simple formula between heat and then the internal energy and change. So the change in energy is basically the enthalpy, if you want to put it that way, which is related to heat. And so we actually want to then measure this heat, then we can see the relation, because we cannot measure the exact value of the enthalpy change or the enthalpy of a reaction, or that's for the reactant or for the product. However, we can measure heat. Okay, so we can measure the heat flow from a system to its surrounding and those stuff. And so we usually use the what you call the bomb calorimeter. That the bomb calorimeter, basically, if you are looking at it, that's where we get the unit for heat in terms of calories. So energy, which is also measured in joules, we can also measure it in calories, which sometimes we shorten it and call it cal. So cal basically is coming from calories, which is also another unit for energy. In this case, the heat energy. A calories basically is just the amount of energy which is required to just raise 1 gram of water by just raising 1 degree, or in other words, 1 Kelvin of a temperature. So if I have 1 gram of water and that water is being kind of exposed to heat, then if I'm able to raise the heat in just say 1 degree Celsius or just 1 Kelvin, then I'm trying to measure the energy, the heat flows. That is where we get the cal from. That's the calories. So in fact, if we want to measure heat, there are some requirements which we have to understand, that the quantity of heat depends on the atmospheric pressure. And of course, we have to have a starting temperature of whatever we are trying to measure, in some cases water. But then if you are going to be measuring the heat of water, definitely once you are going to be exposing the heat, the water to that heat, atmospheric pressure will be influencing it so that it may boil or it may not boil or become warm or whatever. So that's something that we should also take note. Again, to measure heat, we should understand that there's going to be changes in temperature because there's going to be a heat flow. So now we introduce a concept which now describes heat flow and then temperature. So sometimes we should understand that they are not the same. Heat flow is not the same as temperature changes. So if we want to measure heat, we consider that concept of that temperature changes. So a temperature is going to be moving from 1 point to changes from degrees Celsius or Kelvin, and that helps us to measure heat. But again, heat is not the same as temperature. So if we want to really also measure heat, then we have to consider what we call the heat capacity. Now, the heat capacity of a body basically helps us to know the quantity of heat that can be absorbed or released by that body. Are we following?
Yes, sir.
Okay. So when we want to measure heat, I'm giving you the conditions for which we can measure that. Now, I've explained that we'll consider the temperature changes. We'll also consider the heat capacity. That is, everybody has the ability, if I say body, not you, but then a substance which you want to measure the heat of that substance. Okay, so it has the ability to absorb heat or cannot, will absorb or transfer. I'm talking of those that are conductors, heat conductors, not the insulators, the ones that will not allow heat to flow through them. We can't measure, we can't measure their heat. That is why they will not allow the heat. But we're talking of those conductors that can help or can just carry heat through them. So it's either going to absorbing it or releasing it. There we can know the heat capacity of that body. So put that two together, it's going to be leading us to what we call heat measurement. Now again, the last factor or the last component which affects heat has to do with the amount. So we are going to be measuring the heat of a substance. What's the mass of that? That is also going to be contributing to the heat. So for example, you have just a cup of water on fire, and of course the volume of the fire is just the same. I mean, the capacity or the heat of that fire is just the same. So for example, you are using two burners, and the burners, the energy which you are giving is just the same. Now you put on those two burners 1 cup of water and then 1 gallon of water. Which one do you think will heat first?
The 1 cup.
The 1 cup. So definitely what it means is that the mass of the substance is influenced by the heat flow. Okay. So if you put all together, let me put my cursor here. So I hope you can see that. If you put all together, then we'll say that heat basically is just trying to know the heat capacity or the specific heat capacity. When we say specific, then we are just trying to be specific to our object. So the specific heat capacity of that object or that body times the mass of that body times the temperature change is what we are calling heat. So the temperature basically, we are going to be moving from one point to another, and that's the differences will give us the change. And that's what we call measurement of heat. And normally we use what we call the bomb calorimeter. We'll come there again. Well, in a reaction, we can equally also measure the heat capacity. Okay, I mean, we can measure the heat of that reaction. That's where we are going to be saying that, of course, at the end of it, when we measure the change, can either give us, it will be, say, exothermic, or the change will be just endothermic. Okay, so for a reaction, we can only feel the in and then the out of that, the heat in or the heat out of such a reaction. Again, we're going to also deal with that now. Now, for heat capacity or specific heat capacity, these are constants. You don't need to memorize that. So we have done experimental literature values for almost the common substances that we have. Unless it's not common, we can still measure. If it is not common, we can measure the heat capacity, or what you call the specific heat capacity, with a unit of joules per gram per degree Celsius. Okay, if you are using Kelvin, then you should know how we change. How do we change degrees to Kelvin? That's somebody help me. How do we change degrees to Kelvin?
So by adding 273.
Okay, so plus 273 is what we get to have that. So the heat capacity of every body of any matter is just a quantity of heat which can be absorbed or it can be released. And when that experience happens, definitely it's going to create a temperature change. So there's a release or there is an absorption. And that will create a temperature change, which we call a delta T. Okay, so that's something which we should also bear in mind. Well, we can make progress from that. That's when we want to measure heat. We said that we consider the specific heat capacity, we consider the mass, and then we consider the change in temperature. So that's a formula for measuring heat, either absorb or release. Now, if it is going to be absorbed, then the sign of the heat becomes
Hey, is it my network or the lecturer's network?
It's from those things.
I think it's from the lecturer. I think it's out, right?
Sure.
Mommy.
okay. I think it's back. Hello, can you hear me? I don't know why my my network is misbehaving. I don't know. Okay, I guess my screen is on now.
Yes,
Yes.
Okay. Okay. So let's continue. It does happen. That's happening. You see, yeah, sometimes when your in-laws come to me visit you, that will be the day that your salt will finish. So that they will and so don't worry.
They will say you don't know how to cook.
Yes, that's a disgrace this network was to do. Okay. So let's continue. So basically, I guess this formula you can easily remember it. So Q is equal to M times C. Some say C, sometimes it's S. It doesn't matter. What we know is that is the specific heat. Or in other words, the heat capacity. If you are using C, then that is heat capacity. If you are using specific heat, that's where we use the S. So it's commonly called, the heat capacity is commonly called the specific heat. So there is no kind of differences between that. The only thing is that if you are saying specific heat, then you are specific to a particular mass, and that is 1 gram. So the heat capacity can basically be the release or the absorption. That's the heat capacity. But if you say specific heat capacity, then you are referring to specific an amount that is 1 gram between that, but definitely we can use the same. So
Hello, is it network? I can't hear anything.
That's happening again.
It's not even.
Anytime we meet, this man's network will be behaving like this. Misbehaving. This block is not easy.
The call is being recorded, though. The meeting is being recorded, so be guided. Thank you.
Thank you, my sister, for reminding them. Thank you. God bless you. Don't mind them.
Is it raining at 6, please?
Hello.
Yes.
Okay.
Hi.
Yes, sir.
Yeah. So sorry for that. I don't know why it's misbehaving. Okay. Now let's move on. So the difference is just you being specific. So we can equally also say that heat is just equal to the heat capacity times a change in temperature. If you are specific enough, then we should consider the mass which is involved, which is the mass times the specific heat capacity times the change in temperature. Okay, so that's what I want to draw attention. That the change in temperature basically is just going to be the final temperature minus the initial temperature. Okay, so it's equal to C times that cause hello, can you hear me?
Yes, Doc, we can hear you.
Okay. Yeah,
Yes,
so
please.
that's from that. Okay. We can also do what we call the molar heat capacity. Now, if we can measure mass, then definitely we know mass is related to moles if we have that information. Okay, so the molar heat capacity has to do with the heat capacity divided by the amount which is involved. Okay, so that's just one step if you want to bring in the molar heat capacity. It's quite similar to the the specific heat capacity. The only thing is that in specific heat capacity, you are measuring mass. You are measuring the gram of a substance, whilst the molar heat capacity, you are measuring moles instead of the mass. So that's just that. In any case, all these formulas for applying for that is correct. Now let's try one or two examples and see how we can be employing these equations or these formulas. For example, how much heat is required to when?
Please, but I can't see the screen.
Oh, please, I can see it here.
I was in myself.
I can see. Then
This,
you
the,
leave, then
this
you
thing
come
is
back.
visible.
Yes. Please check the network. I can see that. Okay, so it says that it's giving off. Definitely what it means is that at the end, we should be getting somewhere negative. But this is what we have. It says that how much heat is given off when this mass of iron bar is cooled from 94 degrees to 5 degrees, given the specific heat capacity of that ion to be that. So what do you think will be the heat capacity? Well, let me try to see if I can write on this instead of going back and forth on this. Yeah, so heat basically, oh, yeah, so said that heat is going to be equal to the mass, of course, that's grams times the specific heat capacity times temperature. Is that correct? Okay. Now, the mass is
Sir, please, hello there.
okay. Let
Hello there.
me finish too. So please note the question. I'm switching to the whiteboard, please. Okay. So you can see my whiteboard. Okay, so the mass here is if I should go back, is 869 grams, and the specific heat capacity of the iron given at 0.444
0.444
joules
joules per grams degree Celsius.
degree Celsius. Okay, let's go back. Let's see if that is correct.
Yes, that's
okay,
correct.
And the temperature change is from 90. So that's the initial temperature, and the final is 5. So
yes.
if I should go back,
5 minus 95. 4.
The T where we want the to cool down
is 5.
5 degrees Celsius. So we can find change the temperature with the final
5 minus 94.
Minus the what is that? 94. 5 minus what?
89 degrees Celsius.
Minus
my side? Minus 89.
Is
change in time.
Not time, is temperature.
Temperature.
Okay, change in temperature. Yeah, thank you.
The mass is given and the specific
0.444
and the temperature is
minus 89.
89 degrees Celsius.
Yes, can you help us? So what's the answer?
The answer will be
that's in minus
34030.
Minus
34.
034.
No, for me, I have minus 339. So I don't know.
Yes.
Minus
34339.
339, that's what I had.
I had
Yes.
minus 34340 joule.
Wow.
Okay, so 339. So to be so 3 9.6, and it's what be in kilojoules. So we divide by 1,000, so that's 30.
Yeah, 34.34 kilojoule. So you have to divide the value by 1,000. Yeah.
Approximately 34 kilojoules.
Yes.
Kilojoule.
Okay, I hope it makes sense. Now, can you try this one? Let's see. So can you try the second one?
Okay.
They divide by 1,000.
Two minutes. Well, this is even simple. 1 minute to solve that.
Hello, sir. Hello, sir.
So, yes, sir.
Hello, sir.
Yes, I can
Please,
hear
so
you.
with regards to the change in temperature, the change in temperature is from 94 to 5.
Yes.
Yes.
So change in temperature is final minus initial.
Yes.
Yes.
Okay, so that's why we got the negative.
The
Okay,
negative,
I've understood.
Final is 5. So in this case, which one is the final? The example 2, which one is the final?
Okay, the final will be
The final will be
43.0 degrees Celsius.
Okay, so go ahead. So you see the first case, it says that giving off. That's why we got negative 30 something. Now the second one says needed, it will be absorbed. So your answer should be positive.
Okay, sir.
Okay, so what's your answer?
So is it in joule or before, or we should give the kilojoule value?
I had 1469.53 joules.
Yes, that's the answer I got here.
And so when you divide it by 1,000, that should give you 1.47 kilojoule.
Okay. So that's it. For the first one, that's answer. The second one, you said you had what? 146.
9.63 joule.
So is mine correct?
Yes.
Yes, sir.
Okay. So does it mean that question 2, you make use of the specific heat capacity given in question 1? In example 1.
We are talking about water, so we have to give you the specific heat capacity of water, which is 84. Every substance has this notes. That's why we say specific heat. It is in reference to a specific substance. So here, 4.148. Okay, so we have the mass of that water times the specific heat capacity and the change in temperature. The 149 points that. So in any case, for every substance, you should ask for the specific heat capacity of that substance if it is not given.
Sir, please, if the specific heat capacity is not given, or is it going to be given?
It should be given. If you are not given, you can't proceed. It's
But
a
this one,
constant.
sir, we were not given.
This question,
So
there's no specific capacity.
Please check.
The specific heat capacity has been given to us.
Yes. Okay, so I gave you the details below.
Sir,
Okay.
Before here.
Sir, if I understand, what they are saying, the water instead of the 1.182, it has not been given.
Oh, I've given it to you. What do you want again?
But inside the question, it has not been
No,
given.
inside the question, that's why it should be given. If it is not given, request for it. Otherwise, you can't proceed.
Okay. In the exam hall.
Please, in the exam hall, don't go and create confusion there. If you are not giving in the exam hall, so if you are not giving in the exam hall, just so listen to me. If you are not giving in the exam hall, which I should, but if it is not given, skip that question and report back to me. Don't fight with the invigilators. Okay, I submitted the question and I've made a mistake. You don't go and fight the invigilators that they should call somebody or they should find it for you. Once it's not given, skip it. You can't solve that. Okay, let's make progress from that.
That's the only question that you can be doing.
Doc, please, the first question. Doc, please, the first question that we did, my network was worrying me, so I didn't hear something. I want you to help me. What the final answer for the first question? I think I heard my colleague say that they will have to divide something by 1,000 or whatever. I want
that is if you are changing it to kilojoules. So the answer will be given, you'll be getting in joules because of the unit of that specific heat. You'll be getting it in joules. So if you have to report it in kilojoules, then kilo means 10 to the power 3. So you divide by 1,000 to get your kilojoules.
Okay.
Sir, please. The second one, I got 1506.24.
Please, did you use the specific heat capacity? So I've given you the answer there.
Yeah.
The specific heat capacity of water is
4.184.
184 times you are giving the mass of water, which is 12.5 grams. And what's the temperature change? The temperature change should be around 28.1.
20.
Yeah.
20.1.
And what did you say? What did you say you are getting?
So I'm doing it again.
Okay, please do that. As you are doing that, the rest can also try this last one, then we can make progress. So here we have a flask containing this amount of water. Again, as we are going to be using more water, the specific heat capacity of water is 4.184. Although it's a constant, once you use it frequently, you can be familiar with that. Otherwise, if you don't remember, you don't remember, ask for it. Yes, I heard somebody
Yes, sir.
wants to ask a question.
Yes, please. Please, can
somebody asking a question?
Yes.
Go ahead.
Please, if you leave the answer, if you leave the final answer in joules instead of the kilojoules, you'll be penalized. Since heat is energy.
Request is in kilojoules. If the request is in kilojoules, then you have to leave it in kilojoules.
By dividing by 1,000.
Okay. So for example, this particular one, let's leave the answer in kilojoules.
Okay. So, Doc, will it be stated in the question?
Yes, it should.
All right. Thank you.
Okay. Any answer? So we can just move quickly.
217.568.
217.568. Please, did you see that it's 8.0 times 10 to the power 2? Did you see that? The gram. So that's 800 grams times 4.184 times the change in temperature, which is almost like 65. And what are you getting? I'm getting 220 kilojoules.
That's
What
my
did you get?
problem. This question, the answer is so it's 217,568. I try all my me thinking I can get this answer here, but I couldn't. So I put a question mark on it.
Let me confirm that. So the change in temperature from 85 to 20, that's 65.
Yes, sir.
So
Then
the mass
800
and the heat capacity, which is 4.184 times 65.
yes, sir.
Okay, so yes, you are right. So let me correct that. So approximation wise, so they just approximated it in kilojoules. Okay, so it's rather one. So that's okay. So
it's 2.217.
Hello, Mr. Tampuli.
217.5
We are just
8 kilojoules. Yes.
I had 217,568 kilojoules.
Yes.
So
that's the answer.
8 kilojoules, not this one.
Yes, that one is wrong.
Yeah, kilojoules. Is that okay?
Mm.
Okay.
Yes.
Yes, let's make progress. Okay. Now we came across the enthalpy. So that's if we don't take time will just hit us. So just a record of that. So basically what you are just trying to do is that heat is basically equal to the heat capacity times temperature change. Or if you are dealing with a specific heat, then the heat has to do with the mass times the specific heat capacity times the change in temperature. If you are dealing with the molar, then you should know that the molar heat capacity has to do with just the heat capacity divided by the amount which is involved. So just a quick one. Now we can calculate for the heat once we get to have the changes that is happening in that. Now for every reaction which is a thermochemical reaction, a thermochemical reaction is a reaction which is going to be releasing heat or is going to be absorbing heat. When a heat is resolved, the heat, if it is released, then the heat should be negative. When it is going to be absorbed, then the heat should be positive. The same way we can use what we call enthalpy to really look at the change of that heat. So the change of that heat, which is basically the final heat minus the initial heat, can also help us to understand such thermochemical kind of reaction. So we know that if it is negative, that's just going to be exothermic. If it is positive, that's going to be endothermic. So that's a quick one which we have to resolve. I want to just quickly jump to how we can then practically measure the heat. Well, practically, how do we measure heat? And I think you may be doing in your the practical session. So I'm not sure because of the space and then also the reagents available. But then it's under that. Okay, how do we measure this heat? Well, basically the system that we use in measuring the heat transfer we call the calorimeter. And the process of doing that, the process of measuring that amount then becomes the calorimetry. So if you are going to be measuring the heat flow, that's trying to do a calorimetry. And then the calibrated system or instrument which you use then becomes a calorimeter. In a simple way, it's just like you having the siphon cap. I don't know if you know siphon. what they call kako. I mean, when you buy stuff, they put that to preserve a new thing, kako or something. Yeah, basically, if you have a food flax or that, inside that they put that because
is it cock?
It's isolated kind. Sorry?
Is it cock?
Well,
is it like the cock?
No. It's kako. You see, when you buy a brand new refrigerator, there's this whitish light thing inside the box, which actually absorbs the shocks.
It protects the thing.
Exactly.
Is it not the cock?
No.
It's not the cock.
It's called kako.
That foamy, that white this thing that's suspended on the surface of the water.
Yes.
Are you talking about styrofoam?
Yes.
That's styrofoam.
Yes.
The styrofoam the give from the kakonu.
Yeah, I don't know. I never say that's how
white glue.
Please. Is doctor not in?
It seems that his network is gone.
Oh.
This network there.
And this semester, it is not helping us at all.
Very serious.
God should help us.
Na ebusuafo yi nipacho sɛ ɛyɛ sɛ ɛyi ɛba no saa ɛyɛ ne service provider na ɔmo bɛhwɛ aboa anaasɛ ɛyɛ vɛnsɛ UCC fo na ɔmo betumi ahwɛ aboa that's network issue ɛba.
Network providers, because it's a general problem. Also, over here, some of the lecturers, some more call campus, so more offices, some more call at.
Okura okasa no kwa so the article.
That be until. Santuan meeting me.
Obi a networking me.
Santuan meeting me.
Guys, please, I believe you are still recording this thing.
Sister Mercy, you've not said anything bad. We just want the solution. So I'm just asking whether it's from the service providers or maybe from UCC. Say UCC for better, no problem. Then maybe they can help us.
This thing, I'm not too sure that I've said is something bad or I've asked for something that is too bad.
No, I'm not rebuking you. EC code is still there. It means they are aware of it. Me rebuke you. Why? I just want us to stay calm and then see how best they can help us. That's all.
Yes, in the network, yes.
Hello, faces.
Hello?
Faces. Hello.
Yes, sir. Yes, sir.
Find out from him if we cannot more continue so that we'll reset it there.
Okay.
Or how do you see? Because tomorrow we don't have class. Friday too, we don't have class.
Tomorrow we have class, morphology class.
Tomorrow we have
Tomorrow we have
morphology.
class with Dr. Sando.
Yes.
Friday.
But already Friday he has booked it. Already.
He has booked it. Yeah.
He has booked it for us. So that one day.
Why is the class closed?
It's not closed.
No, it's
He's
not closed.
having some challenges for his end.
He's having challenges. I think he's back. He's back.
This will end at 1-9. This will end at 1-9. Just 6:50. So let's take time.
Can you hear me?
Yes, sir, you can hear you loud and
Sir,
clear.
you're welcome.
Yeah, thank you. It's good you take time for me, please. I'm using the MTN table net. I don't know what is the problem, but I've quickly rushed to campus to connect to the cable one. So I think the cable one should be stable now. Okay, so please pardon me. So let's try to move on. And I heard you discussing Friday book. Are you booking it for me? I'll be happy.
Yes, sir. It's for you. Yeah, please, it's for you.
Yes, sir.
Yeah. Okay, so Friday.
Yeah, please, it's for you already.
Friday, what time?
Sir, same time. Same time.
Okay, so 4. So let's
Friday,
make it
5
4.
to 9.
Since
5 to 9.
it's a holiday, you can make it for 2.
Yeah, so let's
11 p.m.
Let it
let's
be
make
early.
it 4. If anything change, we will let you know. Okay, so let's try.
Friday.
Okay, sir. Thank you.
Yeah, so Friday 4. So let's continue. Yeah, so I was just trying to show you how we use the calorimetry or the calorimeter to just measure the heat changes. And we are trying to just see how we can build a simple one from just a siphon kind of a cap. So that won't allow heat to just go through. So it's more or less like an isolated system. But again, it depends on the polymer molecular mass, which will be quite stiff, not creating holes inside to do that. Now, what is the composition of that? We'll see that. So we should have a thermometer to be able to measure the temperature changes. Then we should be, of course, inside the cap, we'll be having water there. So we can know the specific heat capacity of the water. We can also know the mass of the water in there. Of course, how do we know mass? Once we know the density, we can know mass. Definitely we know that density is just mass over volume. So for me to say that I know the mass of water means that I know the density of water, and density of water is approximately 1. So what it means is that the volume is equivalent to the mass. You get it? So if, for example, I measure, say, 50 mil, I can equally say that, well, it's not accurate, but then it's quite close to that amount. So I can equally say that the 50 mil of water is just equal to 50 grams of water. So I'll know the mass of that water. And in that calorimeter, we should be having a kind of a heat. So, for example, we can pick.
Sir, please, are you showing your screen? Sir, please, are you showing your
Yes.
screen?
Yes.
Can you see for me?
Check your network.
Maybe I don't know. Are you using phone or what? Because I can see that. Because I've intentionally connected mine so that if I don't see it on my screen, then it means that
It's
there's
showing.
problem.
It's showing on the screen.
Once I'm seeing mine, means that there's problem with yours. Okay, so we should have say a mass. It can be any substance. Normally we use metal. So we heat the metal, we drop it in a cup which contains. So of course we should know the mass of that metal and also the heat capacity of that metal. So once we mix it, we can just know how the water is going to be changing temperature. So we heat the metal, drop it in that water. We initially know the initial temperature of that water. And then when we drop in that metal, the temperature of the water begins to rise. Or if it is cold, it begins to fall. So that's how come we try to measure the heat capacity of that. So sorry. So with that we can know the differences. So once we know the change in temperature, and of course we know the heat capacities of each, we can also know the heat which is just kind of there. Of course, we use the stirring rod to just stir so that we can have a uniform solution or that kind of measure in there. So what I'm showing here is how the system is going to be gaining heat from an external source, or is going to be losing heat to the external source. So what we should know is that initially we just suppose that we are going to be using a metal. So like the cup, and then we fill the cup with water. Then we fill the cup with water, a particular known volume, so that we can know the mass of that water. And we are going to be covering that so that there's no going to be exchange before that. So before we practice the calorimetry or trying to use that to solve that, in a simple terms, I'm using these systems to just show you. So we are going to be heating a piece of metal. So let's call that piece of metal M. And then, of course, that metal, we are going to be putting it in water, which is a system down. So we can know the temperature or the initial temperature of water to be, say, W. And now once we drop in the hot metal, the temperature of the water is going to be increasing. So it will change from, say, W1 to W2. So we can just make that. So we can use that calorimetry to just study how so it's either the water that is hot transferring its hotness to the metal, or the metal was hot, it's transferring its hotness to the water. So we can just measure and know the temperature differences. Well, we'll get to use the thermometer to measure till we'll see that the thermometer and that of the, so that's a zero flow, and that of the so the solution, metal plus the water, is at equilibrium with the thermometer. So you see the temperature not changing. Initially, when you drop, it will be changing to a point where it will not be changing again. So that's where we can have a final temperature for that. And then we can just measure that. Now, what are we trying to put here? We can measure the heat of that metal, and then we can also measure the heat of water. And you put it together. The first law of thermodynamics says that we can't create, but we can't destroy. So the energy should be just constant. We should not lose it. We should not gain that. So basically, mathematically, what you are trying to say is that the heat of the metal should be a reverse of the heat of the water. In other words, the heat of the water can also be a reverse. If I say reverse, it's just going to be the Q substance of that metal should be equal to the negative of the heat of the water. Am I making sense?
Doc,
And
please can we go
equally,
over again, please?
okay, so sorry. Okay, so to the point where we are trying to measure the heat change, and we are saying that the heat change, we have two substances, the water and then the rod that we have heated. So we heat it outside, then we drop it inside. Later we'll see, so this is just a simple case. Later we'll see what we call the bomb calorimeter. So that's one, the heating is done, then you drop the whole thing in water. Okay, so once we drop it, there's going to be change in temperature. So for the metal, it's going to change its temperature from where it was. So if it was hot, it's now going to be cold. So it will be moving from higher to a lower. Now for the water will be moving from lower to higher. So there's differences in change in temperature. Basically what it means is that there's differences between the flow of heat. Now heat is energy. So basically from the first law, we can't create energy, we can't destroy energy. So what it means is that if the metal is losing its heat, the water is absorbing the heat. That we can't lose it. No, now this is in an isolated system where energy is not moving in and out, and the mass is also not moving in and out. It's an isolated system. So for this isolated system, if the metal is losing, that losing means it's becoming negative, then the water now is becoming positive. So basically the equation here is that if we have a summation of the heat which is involved going on in the calorimeter, what does that mean? It means an opposite of the heat of the water. That means that equal to the negative of the heat of the water. Am I making sense? Okay. So that is what that means. So please note that the heat of the metal is equal to the negative of that. And then what are we doing? We are just applying the first law of thermodynamics, which basically says that we can't create energy, we can't destroy energy. Okay. Well, let's use this to just see if we are trying to follow what I'm trying to say. So for example, and of course, we know the definition for heat. If we know that we are using heat capacity, then heat is equal to the heat capacity times the change in temperature. If you are using specific heat capacity, then heat is equal to the mass times the specific heat capacity times the change in temperature. If you are going to be using molar heat capacity, then note that the capacity divided by moles. Okay, so the capacity divided by moles times the mass, times the mass, yes, the mass, specific. So that's a molar specific heat capacity. So the mass times that of the change in temperature. That's that. So that's for heat. Now look at this. It says that a 360 grams of a piece of steel, which is a rebar, and rebar is used in reinforcing concrete. So that's just something. So that rebar is dropped into a 425 ml of water. Of course, the ml means that once I know the density, and density of water is close to 1, I can know that the mass of the water in that cup is 425 grams. Okay, let's move on. So it was dropping to a 425 ml of water at a temperature of 24 degrees Celsius. And the final temperature of the water was measured to be 42.7 degrees Celsius. First thing that is asking us is to calculate the initial temperature of the bar. Okay, calculate the initial temperature of the bar. What's the idea here? Well, how do I get that? I know that the heat loss from the metal is going to be the heat gain of the water. Do you agree with me? I just mentioned that. So do you agree?
Yes.
Okay. So that's what I've written here. Then we know the formula. So basically what it means is that I need a specific heat capacity of the steel rod. Okay. And I know the mass. So once I want to get the change, then this is what is going to be happening. I want to find, so the change of temperature is a final minus the initial. The initial I don't know, but the final I know. But the same way, I have yes, have okay, specific heat capacity of water. I know the mass. How did I get the mass of water? And the density of water is approximately 1. So that then becomes the mass of water. Now, what is the change temperature? Okay, so I can do that calculation and then.
Hello, Doc.
Yes, sir.
Please, your line is breaking.
Oh, okay. Please confirm. I believe a happy there. They can't disgrace me because I'm using the distance. So please check your network. Here I'm using the cable one.
It's true. It's true. It's true. It's true. Just that the break is just short.
Okay, so it just break and then.
Yes.
Okay. Okay.
Yeah.
So that's joules per gram. Okay.
So, online, that's it. I proud.
Well, I don't know if. Hello, can you hear me?
Yes, sir.
Okay.
Line breaking.
We can hear you, sir.
That's the brother name you see there, sir.
Doc, I beg that thing I've gone basic. I can't hear anything at all.
When he starts using the board with a device for writing, that is when it creates all these glitches. Once he stops,
Then you should use this pen to write because that one was better.
No, are you sure? Can you hear me now?
Yes.
Yes. For now,
so okay. So please,
we're not hearing you say all that you have written. We don't understand.
I'm just writing the information given. Okay, let
the
me
writing we are following.
Let me just use slide instead of writing so that it's quite interesting. Okay, so the heat of the bar is just equal to the minus heat of the water. Now we have definition for heat, which is the specific heat capacity times mass times change in temperature. So we get, so I was just writing the information from the question. Okay, now I have this information. So the information is that I know the density of water to be equal to 1. So therefore, the mass of water is just the same as the volume of water. The specific heat capacity of water is given. And then the change in temperature is also given. So if you want to say my cursor moving, in temperature, we can get the answer here. Now, the river, the mass.
Hello, Doc.
Yes.
Hello, Doc.
So you see, it's not coming from the right.
Yeah, it's true. It's not from the writing. But we'll manage. We'll manage. Let's manage.
It's fluctuating. Okay. For now, okay, it's not right, but it's okay. It should be 3.4 should be okay to hold the video call. Okay. Yes. So I will follow you.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. So okay. Yeah. So that's it. So what then becomes my initial temperature? So I'm just making T1 the subject. Which I'll try to. I've tried to do here. So on the board, that was what I was just trying to put the information across. So if I'm using the board so that we can just get, so the minus initial.
Hey, because I had an interview.
Yeah, same here, same here, same problem.
Just follow the writing.
Let's draw his attention because
Just follow the writing, please. Let's just follow
Okay.
the writing.
Yes, I don't know, but then I don't know why this. So.
Don't continue. We are following the writing.
Hey.
Okay, you let me try that. So the initial temperature, I've put there X. I don't know that one. So that should be equal to the mass of that water. But Assembly. Please give me back a rest. Assembly.
Doc, I have a question.
Restart and then see why the breakage, if it is network. So I'll be back. Just give me some. Let me restart.
Yeah, he's coming. He said we should give him some
Oh,
time.
okay. Oh, okay.
Ghana's network system. Oh.
As I want to me, I took what I took. The network, one is want to took what I took.
Nanso sika no na ọmụ je sika no na ọmụ je so network no ọmụ nye ni yeda uja lodu ya pe na to bandera ape na asa o to credit ape na asa
Togo de mkwede oho.
ma brother bombo de ko na unya akpele na watu bia ma ye bombo de ko to go de ko pa
Normally between 5 and 8, and network near west.
especially during the midweek.
After 8, you can once a dinner, but that time's not the answer.
Hello, can you hear me?
Yes, sir.
Yes, please.
I guess it's better. Oh,
Yes, sir.
okay, so let me share my slide. Okay, so we're just trying to, so let me just quickly use this. So the heat, the summation of the individual heat, which is the heat of the system, which is going to be constant. So that's of there's no heat entering the system. So that's going to be zero. So that we can equally say that the heat, lost by the metal should be the heat gained by the water, or the heat lost by the water should be the same as the heat gained by the metal. So we are just equating the two. And the question is just help. Please, can you hear me?
Yes, doctor.
Yes, sir. Yes, sir.
Yes, yes.
Perfect. Yes.
So the question basically is asking us of the initial temperature for the metal. So with this equation, we can just proceed to find out which one is the initial temperature. So that's what I was just using my whiteboard to try to explain here. And I think before going, somebody said he has a question somewhere.
Yeah, doc, it was me. I wanted to
Yeah,
ask
so go ahead.
the final temperature, is it cut across for both?
Yeah, so they are at equilibrium, the zero flow. Once the thermometer records this, it means that that's the the environment of that thermometer, the water, and then the metal, which is making the thermometer reach to that 42. So that's a final temperature for both the metal and then that of the water. They are thermal equilibrium now.
Thank you, sir.
Okay. So please, can you go through this and see if that is okay?
Yeah, for now it's okay. From your whiteboard, we got it. So we can proceed.
Okay. Yeah, that's okay. Yeah. So let's make progress there. So I jumped one. There are more examples. Maybe you can try
Hello,
more
Doc.
examples. Yes, sir.
Hello, Doc. Please, on the
Yes.
whiteboard, you made you equate density equals mass over volume. Please, can you go over that one for me?
But density, what is density?
Mass
Do you know
per
that?
unit.
Mass on volume. Mass over volume. Okay, and that we wanted to get the mass. We wanted to get the mass of water. Okay, and we said that density is equal to mass over volume. However, the density of water is approximately equal to 1. So if that's the case, then the volume is the same as the mass. So here they said that they dropped that bar in a 425 volume of water. I think if I should go back, they drop it in that volume of water, which is 425 mil. So I need the mass to calculate the heat of that water. So I needed to change this to mass. That's why I brought in the density so that I can get the mass of the water. Is that okay?
Yes, please. Thank you, Doc.
Okay. Now let's take that again. Now, in the calorimeter, there are some conditions that happen there. Well, the calorimeter basically is when it's more or less like an isolated case. There's no heat exchange, and then that's energy exchange, and then there's also not mass kind of exchange. Now, we can get a situation where the temperature is changing, and if temperature is changing, the volume must change. Of course, if the volume is also changing, the pressure is also going to be changing. For example, in typical cases for gases, that's what is going to be happening. But then in the calorimeter, we can have, though temperature is changing and pressure is also changing, the volume can be constant. If you remember that formula, the heat is equal to the change in energy plus, minus P delta V. It can also be a delta P and then the V, meaning the pressure is changing, but the volume is constant. Now, what happens in such calorimeter where the volume is not changing? Well, what happens is that in such a calorimeter, the system basically, or the heat of the system, is equivalent to the summation of whatever is going on in that calorimeter because the volume is not changing or whatever. There's no kind of changes going on. So there's a total heat of the system. And the total heat of the system includes that of the water. It includes that of the metal, in this case we call bomb. And also it includes a kind of a reaction to the water and then the metal going through that more or less like reaction. So that's a summation of that. Now, if there's no exchange of the system, heat between the system and then the temperature, just as the first case, what it means is that whatever the bomb is bringing in is just going to be the same as whatever is going on by the other ones. So for example, if I want the heat of the reaction basically is the heat loss should be the same as the heat gained by the water and that of the metal, in this case, the bomb. If I want the heat of the bomb, the water, the heat of the water should be equal to the reverse of the reaction and that of the bomb. Am I making sense? Well, in that case, what you are going to do is that once I can know the heat for the water, which has to do with the mass, specific heat capacity and change in temperature, I can also know that of the bomb. Once I know the capacity and the change in temperature, when I sum them up, it should be giving me the heat of the reaction. Are we okay? So this plus this should give you the heat of the reaction, of course, in the opposite direction. Well, if we are going to be saying that in such a reaction, what happens if the volume is constant? If the volume is constant, then this is what is going to be happening. The heat of the reaction will not be the same as the enthalpy change. No enthalpy change. Enthalpy change has to do with the enthalpy of the product minus the enthalpy of the reactant. That's what we mean by the enthalpy change. The individual enthalpies of the reacting species, and then so when we sum them, that's why we are saying that final minus the initial. So each of the reactant has their enthalpy change, the heat involved. So if I want the enthalpy change, then the enthalpy of the product minus the enthalpy of the reactant should give me that. Now, at constant volume, that heat is not the same as the enthalpy change. It may be closer, but then it is not the same. It's quite approximately closer to the heat because we are measuring heat. Enthalpy basically means heat change. So what we should note here is that when we say the volume is constant, so if I should write that, if I should recall what we're trying to do, let me open my whiteboard so that you get what I'm trying to say. I want to pray that this thing should not come back. So we are saying that heat is equal to the change in energy plus minus change in PV. You remember this formula? Okay. Yes.
Yes, sir, Doc.
Yes. I can hear you. Oh, are you asking question or I should proceed?
Please proceed.
No, please, I think he was responding to your question.
Okay. I'll prefer if it is not like something that if it's a yes or no, the thumbs up will work for me. But then if you're asking question, you're mute, or if you are answering like a question, not just the yes or no. Okay. Now we can also say that at this point the pressure is changing whilst the volume is constant. Well, if that's the case, if the volume is not changing, that means that the change in volume is equal to 0. So you remember we said that in that case, then the heat is just going to be as the same as the change in energy if the volume is constant. And that change in energy is the internal energy, which we can also have that relation where we have it closer to delta H. So what we are saying here is that when we have a reaction which the volume is not changing, then the enthalpy change is not the same as the heat of that reaction. Again, it may be close. When we say it is the same, so using the words like it is similar, it is the same. I mean, they are not the same. I don't know if you get my construction. So this guy is similar to this boy. They are not like me saying that this boy is the same as this guy. Do you get me? Okay. So approximation in terms of say approximation. Say for example, you have like we just did 217.85 can be approximately the same. Approximately similar to that 218, but it is not the same as 218. So that's something which I want to put pass across. In a similar way, when we have a bomb calorimeter and that we try to say that the pressure is going to be constant. And of course, that's a formula I show you. The pressure is constant, is the volume which is changing. In that case, we'll say that if we go to the same system, we are going to say that the enthalpy change now is equal to the heat of the reaction. If the pressure is constant, that is what happens. So in a bomb calorimeter, where we have a volume being constant, then we can say that what we are actually measuring is not the enthalpy change. It is the heat, but it is not the enthalpy change. So if I should put it this way, okay. So if we have a bomb calorimeter where the volume is constant, then what you are measuring is actually the internal energy, is not the enthalpy change. However, if the pressure is what is constant, then what you are measuring is actually the heat, which is the enthalpy change. And of course, if you ask me why, that's what I just proved. So if the volume is constant, so from that formula, if the volume is the enthalpy is just as the internal energy, is not the heat. It's just the same. Now the question will be, how do we then prepare this bomb calorimeter to do the measurement? Well, if you want to get to have that in a simple lab kind of settings, we just need a siphon kind of cap, what you call the Kako cap, and then we need our water, and then we need a metal. The common use metal that we use in such measurement is magnesium. It heats very fast, and of course it has this bright light which we advise to them not to be looking directly when magnesium is burning. It can blind your eyes, not like you have this photo flash. No, when you flash that, I don't know if you remember, now we don't see those, but then those cameramen taking photos and they have flash. Okay, that can then blind you for some time and then get to have that. So that's how we get to have. So these are the things that we need. Now, how do we prepare that? Okay, we prepare the sample. Of course, we should have a source of heat, which we are calling the fire wire. So we are going to be plugging it, and that is going to be heating up that metal. And that metal is going to be placed in that siphon cap, and then also seal that very well. And then because it's going to be heated up, if we don't take time, it can heat and then get in touch with the surrounding, and then there will be explosion. So we control it with oxygen, okay, so that at least there can be some kind of control temperature there. Now, once we heat the container, we then drop it into, so the container now becomes like a bomb. So like you're having cooking utensil, there's nothing that cooking utensil, and then it is heated up. You pick it up and then you drop it into a pan of water. You can just imagine what happens. There will be that kind of reaction. So quickly we can measure the temperature of that reaction. And that's where we temperature change, and then we prepare that. Well, in terms of analysis, we use these systems to measure that. So that's how come we can just get to measure the specific heat capacities of the various compounds that we have, and then we can give those. So literature is producing those over and over. Now it's going to be accepted when it has been tried over and over, and then we are getting the same thing. Then we all agree that that should be the heat capacity or the specific heat capacity of this particular kind of system. Now, for the bomb calorimeter, we always need to calibrate it, make sure that is giving us a nice curve. So we do the calibration most of the times using some benzoic acid as a sample there. So if you look at it, you have light and cap, whatever sample we are going to be heated. Now we heat that, and then this so that it doesn't go beyond that. So put that together. That's how we can measure the heat capacity. Of course, we can proceed with how we deal with that. Now, from those formulas that I mentioned, say for example, we said that the summation of all the heat in a particular system, so all the heat should be equal to 0. So if we have heat of the water, heat of the reaction, heat of the bomb, that should be equal to 0. So we can find the heat of the others. So for example, we have a sample of a gasoline, which was burnt by using combustion. That is why we are pushing the oxygen around for complete combustion. And that calorimeter with a heat capacity of 10 kilojoules. So of course, here the unit, the kilo must be converted. Otherwise, your answer will be in kilojoules. Now it says that the temperature increases from 100, so it increases. Now what will be the change in energy per gram of that solute? Well, just as we mentioned, here there's an exchange between the surrounding and then the system. In the surrounding, definitely we are giving the heat capacity, a specific heat capacity. If it is specific, then we have to be giving the mass, or we have to use that of the mass. But then we are not giving specific of that gasoline that we are heating, just the specific. So then get the heat of the gasoline which we are trying to heat. Again, we'll see that the heat of whatever the system is getting, we can't create energy, we can't destroy that energy. So if I want that of the system, then it's just going to be the negative of that system, which is just going to give you 1,000 kilojoules. I'm not done. Now the question says that internal energy is measured in joules per mole or per gram. Now it says that what will be the energy change per gram? Okay, so if 50 grams you then what is 1 gram? Do we get that? So that would be the 1,000 divided by 50. So 50 gram gives you that. Then how about the 1 gram? The 1 over 50 times 1,000. That's just the same as 1,000 divided by 50. So we are going to be negative 20 kilojoules per gram. That's one example. Now let's move on to the entire system kind of scenario. Please, any question here? Okay. So any well, okay. I don't have a question, or we are okay. Okay. Just then look at the sample here. So this is another example. This is a reaction type, and that it says that we have a reaction of glucose, which is going to be used as the bomb. And then we have a temperature of the calorimeter rising from this initial to that final. The calorimeter contains water, so we'll be getting the heat of water. And then, of course, that bomb has a capacity, heat capacity of 893 joules per degrees. And the question that is asking us is to find the heat that was produced during the combustion of that glucose. Well, how do we find that? We know that the heat which is produced in this reaction is basically going to be absorbed in the water. So the reverse, the heat of the reaction should be equal to the minus heat of the water plus the heat of the bomb. I don't know if you remember, I just showed you when I was just trying to prove this point that it's just going to give you the same. So, I'm sure I'm online, but then I can't hear.
So we can hear you.
Okay. So that's what you're using to try to solve. So can we try that? Can we try that 2 minutes so that I can? Okay, so try that.
So please, can you give us the specific heat capacity of water, please?
It's 4. Can you hear me? So 4.18. Is that okay?
Yes, sir.
Any answer?
Negative 48, negative 48,700 joules.
You had what? Please check if you had the same answer.
Hello, dog.
Yes. Can you hear me? Hello. So please keep the same answer. Okay. Okay. So how about this one? Can we try this one too? We are following the same approach. Can we do that? Okay. So I'm
Sir,
waiting.
can we have a look at the previous slide?
This one.
Yes, please.
Okay. So what's the question here? Any question on that?
No, sir. I wanted to confirm something.
Okay. So any solution?
So the second one, can we see the question, please?
Oh, sorry. Yes. Okay. Oh, you are still on it. Okay, so what's the answer? Can we make progress or yeah, I should still wait?
No, just give us a moment.
Okay.
Sir,
Yeah.
The formula over there is a benzene formula, yet the question says we should calculate for the conversion of the glucose sample. Couldn't
Oh,
it have
please.
been the conversion of the benzene?
Please, benzene, right? Not glucose. So let me drop that and that. So benzene. So the heat of, yes. So save is benzene rather. Okay. So what do? We calculated the heat of the reaction. I mean the reaction by just noticing that that will be the summation of the heat of the bomb and the heat of the water.
Yeah. Can I mention my answer?
What did you get? Somebody typed 39 kilojoules. What did you get? Did you get 39 kilojoules? Or you didn't get that?
So minus 39.0 kilojoules.
Okay, so it's just the reverse. So the minus there has to do with the heat absorbed or the heat produced. Okay, so here it's the heat produced, so it will be minus. So again, I have to correct that. So that's going to be a negative answer. Are we on the same page?
Yes, sir.
Okay. Now let's make progress. So let's really try to define the enthalpy. So chemists who are always dealing with this thermochemical reactions, which involve these thermochemical equations, do represent these equations with the heat which is being produced or the heat which is being absorbed by enthalpy change. So that's what we usually use to represent that. Now the enthalpy change, I think we have come across that before. We said that the enthalpy change depends on some factors. And some of these factors are going to be, of course, the enthalpy change is an extensive property. So it depends on some factors. So it depends on the physical states of the reactant or the product. You remember when it was solid to gas, the enthalpy change was different. Now, it also depends when we are having the stoichiometric kind of factors. So if a reaction, the original one, is multiplied by a coefficient of stoichiometry, then the enthalpy change must also be multiplied. Again, if you remember, if the enthalpy change, I mean, that's the reaction is kind of changed, where now the product is now the reactant, the enthalpy change becomes a reverse. So if it was endothermic now, the reaction becomes exothermic. So this is just like a recall. So in most thermochemical chemical kind of equation, you see that once, for example, we consider this reaction, 1 mole of that produces this amount. Well, the enthalpy here is minus 286 kilojoules. Now that means that that is exothermic. Sorry, that's exothermic. Now, what it means is that if I should multiply this equation which I'm considering, sorry, by a factor 2, then that enthalpy change must also be multiplied by a factor 2. If I'm going to be dividing by 2, I'm dividing the equation by 2, then the enthalpy change must be divided by 2. Will you remember that? Okay. Now let's make another kind of factor that depends on that. Another factor depends on the physical states of that. Now, if, for example, I'm considering this is in the gaseous form, and if this is the enthalpy change, when I change this to, when I change this to, say, gases, I mean, from gas to, say, solid, then the enthalpy change, it will not be related or will not be the same as this enthalpy. So it's affected by the states of that reactant. Now again, if a reaction is going to be reverse, the enthalpy change will be affected. So if it was exothermic, it now changes to become endothermic. Are we okay? Now, the mathematics of this enthalpy says that, well, we are saying that it's enthalpy change. And for every chemical reaction, we know that we are having an initial going to a final. We have reactant going to the product. So if you want the enthalpy change of a reaction, then it has to do with the enthalpy, summation of the enthalpies of the product minus the summations of the enthalpy of the reactant. That's what we call the enthalpy change. So that's just what we can derive from that. So the summation of all the individual compounds there, their heat. Okay, so when pressure, we are talking of when pressure is not changing. Okay, it's constant. That's where the heat is the same as the enthalpy change. So the summation of the individual heats involved in the reaction, which produces the product, minus that of the reactant, will give you the enthalpy change of the reaction. Okay, so for example, if you have this reaction, and the reaction is methane burnt in air, that's combustion, and produces carbon dioxide and water. The enthalpy change, sorry, who is that a question? Mercy. Can I remember all this? Yes, of course, you should remember all of that. You should remember all the formulas. Yes, otherwise then you shouldn't have come on. And this is, and of course, it's not quite difficult things to remember. I know sometimes when you are aging, it affects your listen to, but I think most of you, it's just for a time. And to you, some of you, it's chew, pour, pass, and forget. So we make sure you chew, you pour, and then you pass, and then you can forget it. But then if you are going to be in chemistry, you can't forget it. You will still be using it. So you need it. And the more you use it, the more you become kind of used to these formulas. Okay, so in this case, what's going on? If we want to get the enthalpy change, then we want to have the summation of the enthalpy change here, which is the heat of the carbon dioxide plus the heat of the water minus the heat of the methane and then that of the oxygen. That will give us the change. Now, when we find out that we did that, then the change gave us a negative value. What it means is that there's going to be a loss of energy from or heat from the system to the surrounding. That's what it means. Now we can equally look at the endothermic reactions as well. Now when we find the summation of the product minus that of the reactant, that's going to give us positive value. So by inference, we can say that if we want to be getting the endothermic reaction, then it means the enthalpy change for the reactants are far bigger than that of the product. In other words, the enthalpy change, the surrounding is bigger than that of the system. The same for endothermic, the reactant is far lower than that of the product. And that's why the differences gives you positive value. So we can find the enthalpy change of a reaction. And that's how we do that. So for example, I have this a thermochemical equation, which I stated earlier. Now, this is how we write it. So it means that the enthalpy change for the reaction has to do with change of the product or the speed of the product minus the summation of the reactant. And the question is this. Let's calculate the heat release by the reaction when you are now going to be having a different level of oxygen. Here, you can see the moles of oxygen here is 1 mole. Sorry, I didn't read that question well. Where is the chat? Okay. I'll be doing that alongside as I saw a pop-up and then I can't see my chat. Okay, let's proceed. Maybe I'll find it later. Okay, the chat. Yes, you are saying that when is it starting to when it is stated the heat is produced, do we need to bring the negative? Yes, when heat is produced, it means that is negative. Heat is given out, it's produced. And when heat is absorbed, that is where it's positive. Okay, so let's move on. Okay, so we have this. Now, if you look at the equation, it says that 2 moles of that oxygen produces this amount. Now, how much of these moles are we going to be producing? What amount? Does it make that? Is it clear? Okay, so basically to find moles of that oxygen is the mass over the molar mass. We have the atomic mass to be 16. We have the atomic mass, so 16 times 2 because we have 2 of that will be 32. So then the moles here is going to be mass divided by 32, we get that moles. And so if 2 moles trying to give us that, then what will happen to our new moles? That's just what we're trying to do here. Does it make sense?
Are you sharing your screen because my own is blurred? I can't see.
I'm sharing my screen and I can see my screen. Okay.
Together on the board.
Okay. So remember these details. So let's go to my whiteboard. Okay, where's my whiteboard? Okay, so let me rule a line. Let me rule a line and then. Okay, so mass of oxygen, right then, equation to get that. So it's that methane plus oxide and 2 moles of water. The enthalpy change was negative 8090 kilojoules. Okay. Now, so what means that 2 moles oxygen produces amount of energy. Does it make sense? Now, using 102.4 grams. Is that correct? Let's see. Yes. So 102.4 grams of oxygen. So let's go back. So what happens if you are using this amount of oxygen, this mass of oxygen? Well, we can only compare moles to moles. So for me to equivalent energy divided by 2. What the new moves? So 102.4 divided by 32. Yes, that's like
3.2.
okay. Now this is equivalent to what? Well, in that case, divided by 2 minus 8 should give me my new energy or my new enthalpy. So this divided by 2 times the minus 890 should give you what? Oh, I thought somebody is doing that for 3.2 divided by 2 times 890 minus 890. That should give you
minus 1780. Minus 1780.
Hey, please. What's 1780? Minus 142.4. Oh, I'm rather wrong. 3.2.
Yeah, correct.
3.2 divided by 2 is 1.6 times 890. Yes.
You are right.
So
You are right. Minus 44.
Yes.
Minus
So
44.
But I had 17 something. Okay. Yes. So are we okay?
Hello, sir. Hello, sir.
Yes. Yes,
Hello,
sir.
sir. I'm not okay. Sir, I'm not okay. Now, from
So
your
why are you?
whiteboard, two from 2 moles of oxygen is equal to negative 890 kilojoules. Now, that
Yes.
890, is it the 390 that is multiplied by 2? If it's 390 multiplied by 2, you will not get 890. Okay, let me ask. Where did you get it?
Where is 390? I can't see 390 in this part. Where are you getting your 390 from?
Sir, please, from your board, delta H from the top after the reaction, delta H is equal to what figure is that? I am seeing it as 3.
890. 890. Minus 890. That's the question. So I was just rewriting it again. So that's minus 890. Can you see that?
Oh, okay.
Okay. So where is the confusion again? So are you okay?
It's okay. Let's
Okay.
continue.
Yo, thank you. So that is the enthalpy for yes, madam.
So you have got the 3.2 rather. That is the molar mass.
The moles of the
So
where from what?
The 2 divided by 2.
Oh, so the divided by 2 is coming from, where's my cursor?
Yeah.
Have you seen it? So this is 2 moles here. 2 moles gives you the equivalent enthalpy of reaction. Now I say that is negative. When you are having a new moles, so the 2 moles is coming from the reaction.
Okay.
But are you okay? Okay.
Yes.
Now let's make progress. So that's again, okay, the answer is there. Now let's look at it. Now we have enthalpy of reaction. If we begin setting this enthalpy of reaction at standard conditions, a standard condition can be a standard temperature, standard pressure mostly. So the standard temperature is around 0 degrees. and then that of the pressure is 1 atmosphere. So in Kelvin, that will give you 273 Kelvin for that. So once we can set these temperatures, I mean the temperature and the pressures as standard condition. At standard mole basically means it's just 1 mole. Standard gram is just 1 gram. So if we set all these things as standard condition, then the enthalpy which you are measuring there becomes the standard enthalpy of a reaction or standard enthalpy of a formation, standard enthalpy of a vaporization, depending on the type of reaction that you are dealing with. Okay, so once what happened? This I don't know what happened. I'm just move back. Okay. Yeah, so the enthalpy change that depends on this temperature and this, of course, we know it depends on temperature, pressure, and then volume. Now, if we set the standard kind of condition, 1 atmosphere, 1 molar, and those kind, then that now becomes an enthalpy, a standard enthalpy of that. Now, we use the small kind of dots there. Where's my mouse? There's small dots there to just explain. Now we are setting it as standard conditions. Okay, so at 25 degrees, that's room temperature. At atmosphere, one moles or 1 concentration, 1 mass, whatever. That's the standard conditions. And that becomes the standard enthalpy of a reaction, the standard enthalpy of a formation, vaporization, whatever, depending on the reaction which you are dealing with. Okay, so we can just get to have that. So for example, if I'm defining the standard enthalpy of a formation, which we just write, so we just use the FR just to show the type of reaction, and not use that it's a standard condition, and then the enthalpy change, which is the summation of the individual enthalpies for the product minus that of the reactant. So that's just that for pure kind of condition. Now let's look at this example. So for example, of course, when I say formation, it's basically like saying synthesis. So we are producing 1 compound or a target compound. So for example, the enthalpy of formation for carbon dioxide. Now this time, the standard enthalpy of formation for carbon dioxide is given as this. And that is for carbon dioxide. Now, if carbon dioxide finds itself in another equation, I know the standard enthalpy of formation for carbon dioxide. I can know that of for water and those stuff. And these are constant values. You can either calculate that. So for example, if I have this equation, this is the enthalpy of formation for ethanol. Ethanol, C2 ethanol. And this is the value for the enthalpy for that formation. We can also move on for graphite. That's just forming a coal. The enthalpy of formation is basically just equal to 0. There's no, they changed the heat for the product is just the same as the heat of the reactants. That's why the formation is 0. So for oxygen, gases, and those stuff, we can. Now, what are we deriving here? Number 1, we'll see that the standard state for carbon in, say, graphite, whatever is the change in temperature is going to affect the product. And so there you're going to see that, well, in that case, the enthalpy of formation is just going to give you 1. Now, if the product should be just 1 mole of a substance, then clearly we can also say that it's also just going to be close. So if the states are the same, then we'll get to have almost the formation to be approximately equal to just 1. So we pay attention to that. Now, in the ground or the elemental form, their enthalpies are just going to be equal to 0. Now, for that, we can create this table. I don't know, it's quite small. And then what I just want to pass across is that we have the standard enthalpy formation of compounds. We can have their combustions as well, the enthalpy of combustion, enthalpy of formation, enthalpy of measure. Later, we'll be visiting this table, which of course you don't need to memorize that, we should be giving. So if you are requesting for any constant, these are the tables which we should be getting that. So for example, if it's in their elemental form, is 0. If it becomes a then you can see there's a reaction going on. Enthalpy to give you that one. Okay, so again, this is where we can be getting our enthalpy of combustion and those kind of stuff. Let's try one or two, then we make progress from that. Now consider this reaction. It says that ozone. Of course, ozone is in the gaseous form, and it decomposes to form this oxygen. And the reaction is endothermic process, meaning the enthalpy change must be positive. The ultraviolet radiation for this, just preamble, whatever, we are not interested. It says that assume that both reactant and the product. So the reactant oxygen, ozone. Assume that both of them, both reactant products of that reaction are in their standard states. That's how we had this standard condition of that. Now determine the standard enthalpy of the formation for ozone. Determine the standard enthalpy of formation for the ozone. Well, what it means is that just look at having just 1 mole of ozone. What will happen? Okay, just 1 ozone. The enthalpy, when we say standard, meaning the mole should be 1, the concentration 1 grams. And so if it says that we determine the enthalpy of formation for ozone, it's just trying to say the standard condition is just 1 mole. So from the if moles give you this amount, therefore then 1 mole will give you what?
So times 2 of it.
You get my idea. So it's not going to be times 2, it's going to be divided by 2.
Oh, yeah.
2 moles. It is 1/2 times what you are looking for.
Yeah, it's true.
Okay. So that's that. So basically, if I should put the answer there, that says that. So if 2 moles gives you that, then 1 mole. So divided by 2, we are now going to get the enthalpy change for that reaction. Does it make sense? Okay. Now, for your a little bit, I want to see how you can write equations for the enthalpy of formations for that. Of course, if you don't know the exact values, just let me know. I mean, ignore that, but just note that this is enthalpy, and mostly the enthalpy of formation can be positive or it can be negative. So if you are going to be writing the enthalpy of formation for okay, let me start from this way. Let me start so that you get what I'm trying to do. So hydrogen gas reacts with chlorine gas to produce this hydrogen chloride, in other words, chloric acid or hydrochloric acid. What is the enthalpy change for just 1 mole of this hydrogen gas reacting with 1 mole of chlorine gas to produce just that amount? Okay, so if we want to do that, what is just asking us is to just write the equation here. So let me go back to that. And it has given us the enthalpy and it's asking us 1 mole. But then when we write the equation, we can know what 1 mole is going to give. It says that gas, and then I want to balance. In this particular point, balancing equation is quite useful because we are going to be using the moles to be compared. So how do I balance the equation? If I should put 2 moles here, that is going to be balanced. Is that correct? Okay. And that okay. Well, so that's it. Now it's now telling us, please, is that okay? Okay. Is somebody asked?
The 92. Yes, sir. The minus 92. I didn't get it.
It says that if the standard, so if 1 mole, the standard condition. Okay, let's go back to the question. So let's go back to the question so that you get that. This is the question. Okay, what will be the enthalpy if 1 mole of this reacts with 1 mole for a standard state conditions? And that he has given us the standard enthalpy formation for HCl.
HCl, which is negative 92.3.
Did you see that?
Yes, please.
Okay, so if you are going back, and this is standard though, and standard means the HCl should be 1 mole. So what it means is that for this 1 mole, I need to divide this by half, and this by half, so that this becomes 1 mole, and this is the enthalpy. Okay, now the question is, what happens if it is going to be 1 of this, the mole of that? Basically, what it's trying to tell us is that 2, so multiply this equation by 2. If you multiply 2, I'm going to be getting hydrogen gas acting with gas.
No, we are not hearing you.
Divide, which is now could be 90.3.
Doc, please, your line is breaking, please.
Again, by you see what I've written.
Yes.
Yes.
Okay, so 92.3 times 2 is approximately 8.6 kilojoules per mole. So that's 1 mole of each of them. Does it make sense? Or so if you go back to that, yes.
We are multiplying it by a negative number, so I think it should be a
By 2.
1.
I didn't multiply by -2. The negative was already there. I just put the negative side, negative in front of the number. So
okay, sir.
Okay. So that's what we have done here.
Sir.
Yes, sir.
Sir, should it have been per mole, kilojoule per mole, or just kilojoule?
Yes.
Because kilojoule per mole.
Yes. The unit there is kilojoules per mole, not just kilo.
Oh, okay. Okay.
Okay. So sometimes it's good I do this correction, see if it's going to be confusing before I continue. So kilojoules per mole. So kilojoules per mole, and then I think there was one, two. Yes. So we don't get confused if. Okay. Yes.
Hello, Doc.
So that. Yes,
Hello,
sir.
Doc. Hello.
Yes. Yes.
Please, on your whiteboard, why do you multiply the reaction by half?
You see, we are talking of.
The whiteboard, you multiply.
So look at my. We're looking at the entropy of
this network.
HCl. That's the formula. There should be 1 mole. Standard means 1 mole. Please, the others, can you hear me?
We can hear you now.
Yeah, so the standard
But we can hear.
No, breaking is breaking.
No, it's when you are talking that the thing is that breaking.
I have realized that listen, when he is writing and talking, he should finish the writing and just explain.
It's just a network. So so the standard HCl is going to give you 1 mole of HCl. So if I want to write so that I'll get 1 mole of that, that means that
I can't hear anything at all.
Okay, so but you've seen what I've written down, don't so let's so that's how we multiply by 2. So if I want 2 the chlorine mole of hydrogen, basically 2. And by multiplying by 2, I can then get the delta H to also be multiplied by 2. Okay. Now if we understand that, let's try to write so that you get to understand it. Let's write the enthalpy of formation for the following reactor. I should have made it a standard enthalpy so that you know 1 mole of that. Okay, if I say enthalpy of formation, you can just write the balance equation. But then if I say a standard enthalpy of formation or heat of formation, then the product should be 1 mole. Please, did you get what I said? If it is standard and standard formation, then the product that is being formed should be 1 mole. But then if it is just enthalpy, that's just going to be like the balance equation. Are we okay? Okay, so if you want to try this, just to A and B, let's move on. A and B, the rest, when you get that, you can try that. But if you want to write that, it's going to give you, so the question should rather be the standard heat formation, so that I'm going to be getting 1 of the system. So in this case, which will affect the enthalpy change of that of the ethanol. Okay, so that is that. Now, just as a summary, we are trying to delay on this first law. Okay, so the summary here is that if we want to have the standard enthalpy, we are looking at just having the enthalpy of the product minus that enthalpy of the reactants. So we can just calculate that. So it means that if I know the individual enthalpy of formations of the products, sum them up, know the enthalpy of formation for the reactant, sum them up, then the difference will give you the enthalpy of a reaction. Okay, so for example, I want to calculate the standard enthalpy of this reaction. Well, if I want to calculate this, what it means is that I should know the enthalpy of formation for hydrogen gas, know the enthalpy of formation for nitrogen gas, then know the enthalpy of formation for ammonia gas. So that now the enthalpy change for the minus the individual enthalpies. I hope you can hear me.
Doc, if you can come again, your this is I've gone we can't hear. If you can come again, please.
Okay, so we are just going like this. Okay. So I want to find the standard enthalpy of, and it's standard because we are going to be using standard formations. These are standard conditions. So if I want the enthalpy of a reaction, the standard enthalpy of a reaction, then that has to do with the summation of the individual enthalpies of the product minus the individual enthalpies of the reactant. Now, for accuracy, normally for accuracy, we look at activity and the reaction activities, but we are not considering that here. That's why the reaction considers that activity there, but that's not important. Okay, so I give you an example that if I want the enthalpy of a reaction for this particular reaction, how do I get that? I need to know the enthalpy of formation for the product minus the enthalpy of formation for the two reactants. Okay, then the differences will give me the enthalpy of the reaction. So this is a formula. Product minus reactant. Now, what's the enthalpy of formation? It's a standard system. I mean, it's constant. It should be given to you. So the enthalpy of formation for that's 1 mole of that is given, and here in the equation is 2 moles, so multiply by 2. So if 1 mole is giving you this, then how about 2 moles? Plus, so we are looking at that's a product. The product is only ammonia, minus the summation of that of the hydrogen and that of the nitrogen. The moles for the nitrogen is 3. So if you want, you multiply by the standard, because the standard was 1 mole. So if 1 mole gave you a value, then how about 3 moles? Okay, now these standard formations are constant. So I show you the table there, so we have to provide them. Okay, so we just know that. Now for elemental form, we said that the standard formation of elemental form mostly is just equal to 0. So the enthalpy of formation for hydrogen is just 0. That of nitrogen is also 0. But for the ammonia, the value is given. Okay, so we can check from the table, we can get for the enthalpy of formation for the ammonia. So if I should come here, the enthalpy of ammonia is somewhere. Okay, so these are elemental form. So this hydrogen gas. Okay, so the table extends. So this nitrogen ammonia is 46.3. You can see that. That's the enthalpy of formation. Enthalpy of hydrogen gas is 0 for elemental form. Where is hydrogen gas? Yes, 0. Enthalpy of nitrogen gas is also 0. Where is nitrogen gas? Yes, so that is also 0. Okay, so that's nitrogen gas. Yeah. That's also 0. So if I have this information, then definitely the enthalpy of reaction is just going to be the enthalpy of formation for ammonia times 2. Okay, let's do real example. So look at this question and see if you can solve that. Calculate the standard enthalpy of combustion for this ethane at 25 degrees Celsius. That's what you are looking for. Now he has given you the enthalpy of formation for that ethane, he has given you for carbon dioxide, he has given you for water. For elemental form, oxygen is going to be 0. So that's why they didn't give. So what do you think will be the enthalpy of this reaction, which we call the combustion reaction? I hope you can do that.
So, it's a question I wanted to ask. I think if he's not giving the question, we assume that is 0, right?
You should just know, not just assuming. I'm stating that for enthalpy of formation, the standard enthalpy of formation for elemental molecules are all going to be 0. So I cited these examples there. So oxygen, elemental oxygen, hydrogen, nitrogen, the elemental form like silver and its elemental form are all going to be 0. So when we don't give you, just note that they are 0. If you are getting confused, you just ask, but then note that it's 0. So can you try this so that you tell me what will be the enthalpy of the reaction? That's a combustion reaction. Standard one. Any answer? Yes, any answer?
Just 1 minute.
1 minute.
Say.
Yes. Yes.
I have here negative 3,115.6 kilojoule.
116 or 115. So 3116.6.
Okay. Let's check. But 3115.6.
Okay, 0.6. Okay.
Yes, please.
I think it's quite closer. So if you are like changing that to kilojoules per mole, what will be that? That should be 3 points. I think 3.2, 3.1 kilojoules.
3.1156.
So yeah, so 3.1 kilojoules.
Yes.
Yes. Okay. Well, let's go through together if we are done. So we are saying that we are going to be looking for the enthalpy of the standard enthalpy of this reaction, which is the ethane plus oxygen plus, which gives you carbon dioxide. So that's combustion reaction. Now we're given the enthalpy of formation, the standard enthalpy of formation for the ethane for oxygen is 0 because it's an elemental molecule. Then for carbon dioxide we're given, and that of water we're given. Now if you look at the enthalpy of reaction, it should be then the summation of the individual enthalpies, which is for the product, minus the individual enthalpies for the reactant. Is that okay? So that is it. Now, what's the summation of the enthalpies of the product? That is 4 times the enthalpy of formation of carbon dioxide plus 6 times the enthalpy of formation for the water, minus 2 times the enthalpy of formation for ethane, well, plus 0. That's just not going to. So the answer should, so that's a formula. So the summation of the product minus that of the reactant. If you then put in the values, then you should be getting approximately 3.1 kilojoules per mole. Does it make sense?
Yes, sir.
Does it make sense? Okay.
Yes, sir.
Okay. Yes. Well, let's make progress. So what it means is that once I know the standard, and again, standard means 1 mole. So if there is now another mole to that, then that's why we're multiplying that. Another first law, then we can look at what we call the Hess law. Under the same first law where we are not creating energy, we are not destroying that. Then it's just the same way. So Hess law basically tells us that in a series of a chemical reaction, so like series, this one produced that to produce that. When we go through all this series of the chemical reaction, the total amount of heat which is involved is just going to be the summation of all the heat that is involved. Because we can't create heat, that's energy. We can't create heat, we can't destroy that heat. So for example, I'm showing you this graphite to carbon dioxide. Well, from graphite, we can burn graphite, then we produce carbon dioxide. Equally, we can do what we call the incomplete combustion. We can equally say that we have carbon monoxide react with oxygen, we can also produce carbon dioxide. And if I want the heat involved in these two productions, then these 2 ways must kind of come together. When we sum it up to give me the total heat which is involved in the carbon dioxide production. So in summary, Hess law basically tells us that irrespective of the steps that we take, the heat of that production must be the same. So that will be the summation of the individual steps that we took to produce the product or to give us the product. Are we okay? So if, for example, step 1, we could use carbon and oxygen to produce carbon dioxide, we can equally break it down. Oxygen, and that's in incomplete combustion will produce carbon dioxide. If the oxygen is still in excess, we can produce carbon monoxide, and then reacting with oxygen again, we'll have to have now what is the heat change of the carbon dioxide? It has to do with the individual summation. So from carbon to carbon dioxide plus from carbon monoxide to carbon dioxide will be the heat change for that. Okay, that's S law. So basically, say for example, I have this equation there. It says that we should use this equation to produce this. So find the standard enthalpy of formation for calcium hydroxide. Well, how do I find that? Once I know the individual formation which leads to that, summing them up will give me the enthalpy of that formation. Well, how do I sum them? I have to sum the equations, and by summing the equations, I should be getting the formation of calcium hydroxide. So there are sometimes I have to multiply some equation by a factor. There are sometimes I have to reverse that equation. Okay, so you remember, if I multiply by a factor, I have to multiply delta H. If I reverse it, the sign will have to change. You get me? Okay, so if, for example, in this case, if I want to find that of the calcium hydroxide. I have calcium hydroxide here. Okay, so what it means is that this can cancel this. So the calcium oxide cancel calcium oxide. Then water is in the reactant, it cancel this water. Then we can then add it. So the total equation will be calcium plus hydrogen gas plus oxygen to give you a calcium hydroxide. So then the summation of that from Hess law, we just need to sum them up. So for example, the total enthalpy of formation of calcium oxide should be in this form. Calcium plus hydrogen gas plus oxygen, the equation is balanced. 1 mole to give you an enthalpy of formation. We don't know. We could make reference from the table, but this time we are calculating that. Now from the reaction, we can find out how we can get this overall reaction. And the overall reaction, we are going to now add all their enthalpies to get the enthalpy of that reaction. Doesn't make sense. So the enthalpy of formation for calcium hydroxide is just summing the individual enthalpy. Again, if their equation is not summing up, some of them sometimes you have to reverse the equation. By reversing the equation, the enthalpy must be reversed. Some of them you need to multiply by a factor.
Say.
Yes.
Sir, please, what is then what we are seeing right now? Please take your time for us and go through with us, because I'm seeing some cancellations.
Wait, are you sleeping? So when you just woke up, you
saw...
so you just have not said anything about cancellation.
Can you sleep? Sir, can you sleep while this thing is there?
Yes,
this thing you cannot sleep.
The others will bear record that I have not mentioned anything about it. So maybe you were sleeping. When you were just woke up, you just saw the lines.
Sir, I have not been sleeping. I haven't been sleeping. Please, now let's look at it.
I'm just fully alert. So that says that. Now I'm here. That when we sum the equations, the enthalpy of formation must be the summation of all the individual enthalpies. Now, how do we sum the equation? We should get the overall, or that is our target equation. Okay, so if you look at it, we have 3 different equations. How do we get this our target equation? That is, we are summing them up. And that's why I'm saying that this one is just straightforward. There are some cases where the equation, you have to turn it before you can get your target equation. Reverse that. And when you reverse it, don't forget to reverse the sign. Now, there are some equations you have to multiply by a factor. When you multiply that equation, don't forget to multiply the enthalpy also. You get what I'm saying? Now, how do we get that? We have equation 1, which gives us this delta. We have equation 2, that gives us that, and then equation 3. How do I get this equation? You see, when we have a reaction where the reactant is the same as the product, then there's no reaction going on. In that case, that reactant is going to just be a spectator, or it can just be an intermediate. So for example, from equation 1 to equation 2, calcium oxide is at the product side. It's also appearing at the reactant side. So we have to just cross that. It's just sharing the reaction. It's not part of the reaction in producing calcium hydroxide. It's just a spectator reagent. We just like you go to the football pitch to watch ball. Those that are much concern are those that are playing the football on the pitch. You are sitting outside the I mean, you are just cheering the game. You are not part of the game. But if you don't go, the reaction, the football will not be nice. So if they are not there, the reaction will not be complete. But then they being there does not influence the reaction. So we cross them out. So when they are the reactant side and then they are the product side, we cross them out. So calcium oxide can cross out calcium oxide. Now there's water at the reactant side. There's also, so the arrow is what we are using. And there's also water at the, so check the number of moles. Here the number of moles are the same. That's why we could just easily cancel that. So the water can also cancel water. What I'm left is calcium, oxygen, hydrogen, oxygen. So I add everything together. Calcium is 1, hydrogen is 1, oxygen is half plus half, which gives you 1. Then what is left at the reactant side is calcium hydroxide, which is the target equation which we are looking for. So it means that we just sum them up to produce this amount.
So could there be instances where, for instance, with the water you cancelled, there could be differences in their moles? Let's say 2 moles of water in the second equation, and then 1 mole of water in the third equation. In this particular instance, what do we do?
So that is where I'm saying that there are some equations which you have to multiply. So if at the end the overall reaction which I want does not include water, and I want to get rid of the water, then one of the equations must be multiplied. So if the first equation has just 2 moles, the second equation has 1 mole, then I need to multiply the third equation by 2 moles so that I can cross out the water. They are not part of the overall reaction. And that's where I'm saying that when you are multiplying that equation by 2, don't forget to multiply the delta H by 2 also. You get it?
Yes, sir.
Okay. So that's just that. I wanted to, I'm just checking my time. I wanted to see if I can get you are switch, right? Switch, and this is 203. All right, so I want to find another example for you. It's not on the slide. I just want to generate one for you quickly. I don't have it on my slide. That's so I just want to, yes, sir. So yes, you can go ahead, please.
Please, this one, are we done with it?
Yeah, so no, we are not done. So the answer will be the summation of the individual delta H. So that's the enthalpy of formation for calcium hydroxide is minus 986.5 kilojoules per mole. Are you okay?
Okay, sir.
Well, I'll try to find my files very well. So I can give you more examples. Otherwise, you can equally also find some examples to try, and then you can just make this one. Okay. So having said that,
so sir,
yes, sir.
Please, so what happened to after we had canceled these moles out, the equation you have had like calcium plus oxygen
that's
plus,
the target you are looking for. That's the overall reaction. That's the overall reaction. That's why initially I asked you to write the enthalpy of formation for some compound. So that becomes your target you are looking for.
Okay.
Okay, so the question was that we should calculate the enthalpy of formation for something. So once we know the equation that leads to that enthalpy of formation for that thing, we can now calculate. Yes, I hear Kurum. Please, Ask your question now. As
sir, I wanted to ask the oxygen. I think they are the same, but they were not able to. We didn't cancel that one.
We didn't cancel because they are all at the reactant side. If it happens that like one of them was at the product side, then we can cancel it.
Okay.
But then they are all at the reactant. That's why we sum them up.
Okay.
Okay, please, other questions? I'm still waiting on. I want to be ending very soon, so I'm waiting for your question or clarity. You want to clear some. Okay, so the decision is that we are meeting on Friday. You said 4.
Yes.
Okay, so please, although we know that it's a statutory kind of public holiday, but I know by that time you have to enjoy yourself, so you can also come and learn small. Okay, so that is just that. You can find much example to try. Okay, so the next time we'll just be continuing with the first. I wanted to, if not for the next, I wanted to end the first law today, but then I'll end it and then continue with the second and the third law. Yes.
Since it is a public holiday, will we get called to do the recording for us?
Well, if we don't get it, I can create so that's okay. I can send you my own link, which I can report.
Okay.
Okay.
But that's
please.
Not a Google Meet, because the pro Google. I have the team, the 360, so I can send you the team link, and that one I can report.
Okay. Thank you very much.
Yes. However, I think the guy is here, so he will take notes. I think he will be available to do the recording. Yes.
Look, if you look at the translation that has been done, is it the fact that the custom was cancelling the custom in the second equation, and then the water was cancelling the water in the third equation?
Okay. Yes, but let me just see if I can. So back to my whiteboard there. So I just use this to close. I know it's late, but then so we have calcium plus oxygen, oxide. We have calcium oxide plus water, giving you calcium hydroxide. Then we have hydrogen plus oxygen, giving you water. Now, how do I do the calculation? Basically, what I'm just doing that you see the arrow here means that this part is the reactant, this part is the product. This part is the reactant product. This part is the reactant, this part is the product. So an easy way to do this is to list all the reactants as one side, then list all the product at one side. Then you see the common factors there. If one appear at the reactant and appear at the product, it should cross out. Okay, this is straightforward. That's why I can do that. So I will list all the reactants. The reactant there is calcium plus half of oxygen plus calcium oxide plus water plus hydrogen gas plus oxygen, another oxygen 2. Now, all of the reactant here, calcium oxide plus calcium, plus calcium hydroxide plus water. You see that? Now, at the product side, I have calcium. At the reactant side, I have calcium. At the product side, I have water. At the reactant side, I have water. What is left? What is left is this plus this, this. So that gives you one more. So what is is calcium plus oxygen, half plus half, that is 1. Then plus hydrogen gas. That's the reactants giving you products. Which is only calcium hydroxide. So that's what we just did.
Okay, Doc, you can see that the oxygen was left out, and it was twice. So you decided to just pick 1 instead of writing the 2.
Yeah, so it's half plus half. We are summing them up. Half plus half is what?
Okay. 1. All right.
Yo.
Doc.
Okay.
Doc.
Yes.
I think the one you did is better than this one.
Please,
yes.
I would like to chip in this. You see, anytime you are not using the whiteboard, I think you flow. There's no breakages or there's little breakages. But the moment you begin to write on the whiteboard, then there's some kind of distortion. So I'm pleading that in our subsequent meetings, you try to work on it for us so that we enjoy it freely.
No,
And also,
I believe the network. I believe the network because the whiteboard is giving us more understanding.
It's the network.
I was also
So
saying
this thing is breaking. It's the network.
I also realized
it's
that
network.
when he finished writing on the
Doc, we like the whiteboard. We like the whiteboard.
Because
So who is
this
talking
is
now?
physical
And who
chemistry.
are we hearing?
The writing helps in following. No, when you are doing calculation and you are just saying it. So normally at the regular level for physical chemistry, I don't even use PowerPoint. But because I'm doing online, and that's why I'm using the PowerPoint. So for physical calculation stuff, when you are writing as you are explaining, it's quite simple to follow than just following this one and trying to explain that. So that's why I'm using the whiteboard in writing. However, today it just happened that the network was bad. Last week you didn't experience that. So that's why I use both. So I show you, then I go back to my whiteboard to see what you are doing. So let's pray that the network is stable on Friday. God willing, if it's stable. If it is not stable, then we'll just stop the whiteboard.
Sir, is the last.
Thank you.
I can't say the last question, but let me ask this. Please, in the case of the half moles of the oxygen, in the first equation and then in the third equation, assuming there were 2 moles of oxygen gas in each, it means that of course, because they are on the same side, you are going to add the 2 to give you 4 moles of oxygen gas.
Yes.
Okay.
And if they are at the opposite side, I'm going to cross them. If they are of the same mole, I'm going to cross all of them. If they are not the same mole, but then in the final equation, I don't need them there, then I have to find a factor which will multiply that equation to get rid of the 2 from both sides.
Exactly.
Doc, under what condition are we supposed to reverse some of the equations?
So the condition is that you target this the enthalpy of formation. So if a reaction is not falling, so for example, let's I hope you don't mind if I extend the time.
Yeah, okay. we are with you.
Continue, sir.
Okay. So if, let me clean this and give you another equation. So a new one. Okay. Say for example, this is the equation. So calcium plus oxygen, and always check if the equation is balanced. Don't assume that every time you write equation is balanced. And the enthalpy here is enthalpy 1. The value is there. Then we have calcium hydroxide. Okay, calcium hydroxide giving you calcium oxide plus water. Is that okay? Then we have, say, 2 moles of hydrogen gas plus oxygen gas, giving you 2 moles of water. And this is
Doc, bro, your screen is not coming in. It's not showing.
It's showing.
It's showing for me. It's showing for me.
It's showing.
Okay, so this is another question. We are giving the values of this. Now it says that we should calculate the enthalpy of formation for calcium hydroxide. Okay, calcium hydroxide. The enthalpy of formation for calcium hydroxide. Now, what is enthalpy of formation? How do I write enthalpy of formation for calcium hydroxide? Well, what's the component here? I have calcium, oxygen, and then hydrogen. So therefore, the enthalpy of formation, 1 mole of that. I need just 1 mole of calcium hydroxide. So I use calcium 2 plus oxygen 2 to just give me calcium hydroxide. And this is the enthalpy of formation, standard enthalpy of formation. Now, this is the target. This is the target I've been asked to calculate for. Are you okay?
So will the target be given to you?
You have to, if they don't give you, the question says enthalpy of formation. So that's why I initially gave you how to write enthalpy of formation for compounds, so that you know the equation. However, if you don't know, then you should find a way of knowing. Sometimes they give you the equation, but then once they say standard enthalpy of formation, you should get the idea that it's forming just 1 compound. So you just look at the elemental form and then put synthesis, put the individual elements, you just form 1 compound. If you don't have any idea how that equation will look like. So I of formation for calcium hydroxide. Element there is calcium, oxygen, and then hydrogen. So the elemental form, calcium, hydrogen, oxygen. Then I have calcium hydroxide. That's the enthalpy of formation. So the question is, what is the value of this? Now, if I come to this equation, I need to make sure I'm going to getting this particular target. So look at the first equation. The first equation of calcium in the target, I have calcium on my right. I'm not going to do anything to that first equation. And that's the calcium is 1 mole. In my target, the calcium is also 1 mole. So for the first equation, I'm not doing anything. Are you okay? Now the second equation. On my target, the calcium hydroxide is on my right. Now equation 2, my calcium hydroxide is on my left. So I need to reverse equation 2, this equation. I need to reverse it. Okay, so if, for example, this one, the value there, okay, let me put some values here. So the value here was negative 65. The value here was negative 365 or 366. The value here was negative 286. So I need to reverse equation 2. Now, when I reverse equation 2, it becomes calcium oxide plus water, now giving you calcium hydroxide. And the reason for reverse is that if I check my target, and then I check where I can find my target, the equation looks like it has reversed. Now, in that case, I need to reverse the delta H. It was positive here. So when I reverse it, it becomes negative 65. It was positive 65. Are we okay? So for the first equation, calcium plus half oxygen giving you calcium hydroxide, I didn't do anything to that equation, so it still remains 3 minus 3 6 and 5 6 minus 3 6 5 and 3 6. Okay, now if I like my third equation, look at hydrogen here and look at hydrogen on my target. Yes, hydrogen is on my right, but if you look at my target, I need 1 mole. This equation says that the hydrogen there has 2 moles. So what do? What I'm going to do is that I divide it by 2. I'll divide by 2 so that I can get 1 mole for my target. So divide that equation, divide it by 2. So that I divide by 2. Now hydrogen becomes this, oxygen becomes this, and water now becomes this. And that means that delta H or the delta 3 must be divided by, so whatever value of the 286 must be divided by 2.
Please,
Is that okay?
the third one, I'm confused. Third one is just, I didn't get the explanation.
Just say that hydrogen should be on my right. Hydrogen the third equation on my right. Next, my target says that the hydrogen should be 1 mole. But then in the third equation, hydrogen is 2 moles. So how do I get it to be 1 mole? Don't I need to just divide by 2? So I divide the whole equation, not just one element, though. The whole equation divided by 2. So it means that hydrogen divided by 2, oxygen divided by 2, water divided by 2, then this delta divided by 2. So that this cross that it gives you 1 mole, this would then give you half mole, this would give you 1 mole. Okay. Now I can sum them up to get my target. Sum them up, all the reactants and then all the products will stick out some of that will appear on both sides. And they are the same moles, so I can cross them out. Water are the same opposite side, the same moles, I can cross them out. It's half some plus hydrogen 1 mole plus half. That is what I'm getting here. And that means that once I can now sum the equation, the enthalpy of formation is now the summation of all. So that is 1 plus 2 plus enthalpy of 3. Yes, so that is it. Please try to get an example to solve. I think we have to drop the curtain here. We'll continue with a similar trade, which will be talking of the enthalpy, bond enthalpies.
Yeah, please, Doc. What you just did, my screen gone off. If you can send your board, your listen to WhatsApp so that we can look at it.
Oh, my screen is on,
your
so
board,
I don't know.
Please take screenshot. No, my own is not that. I can't see. I tried several times. My network is very bad.
Don't worry, you will have the recorded listen. The recorded listen. So you can play it anytime to see those things. So don't worry yourself. Yeah.
Yes. Please, what if the reaction, the equations given? You know, we have 2 types of reaction: reversible and non-reversible ones. What if the equation given is an irreversible equation? How do you approach that?
When do you know a reaction is irreversible? I'm sure you know what you are saying.
When a total new product is formed, in the final and that means that reaction is irreversible.
How do you know? You are a chemist. Talk like a chemist. How do I know a reaction is reversible? It's not reversible. How do you know?
That is
when you use the arrow. Once the arrow is pointing one direction, it's an irreversible reaction. Once the arrow arrow is pointing opposite side, that means that the reaction is reversible. So what's your point?
Okay, thank you. I get you said that. Thank you very much, sir.
Okay. So you reversing an equation.
I'm boring.
It's not like a reversible, irreversible reaction. Okay, so see you. My home is far from campus. I have to go. It's late. So see you on Friday.
Thank you, sir. Sound sleep, Doc.
Okay.
Thank you.
Bye-bye.
Thank you.
abusuafo remember Friday ibisia oi ambrabo mi hu se mi nko se yi na
Francis when you come on
many bad yakom bra many go
afọ ni so
wait me ko si pa ma ko gina hana chere mi da tena sai so yi biology major sai so chemistry ni economic chemistry ya
ebe yi why
Rahu. Ebefa. Ibisha. Mo amuti ase mo ya ati. Ebefa.